So we're still going to be talking about them. And we can also look at some strategy for solving exponential equations. So let's try solving another one. Let's try this one on for size. Now, you're probably looking at that and you're saying, you know, what is that? What is going on with this? Well, again, our strategy last time was to try and see if there were any numbers or if we could rewrite the expression in a manner that it was ultimately just an exponential equation with the same base on both sides. Because if we can do that, then we can rewrite and we can equate the powers. Because unfortunately, the variable here is in the exponent. So the variable's in the exponent. Well, it turns out you are going to be able to do that if you make a few connections. Perhaps a base of 2 will be appropriate here, because 4 is actually 2 squared. 32 is actually, we'll try it out. Let's see, 2 times 2 times 2. Oh, 32 is actually 2 to the 5th power. So there's a few connections we can start to make here. The first one is that 4 can be written as 2 squared. And then 32 can be written as 2 to the 5th. And then one more connection we're going to need to make. It's almost the way we want. It's almost how we want it. But notice here that the 2 down here, the 2 up here, this is in a fraction. But that's okay, because if you remember how negative exponents work, negative exponents actually are the number of times we are dividing by. So actually, this expression here inside the parentheses, we can bring the 2 squared up to the top here by making it 2 to the negative 2nd power. That's a negative sign. And now if we keep going, we'll have to come over here. According to our exponential laws, this is 2 to the negative 2nd, then raised to the xth power. We can multiply. We can multiply these two powers. So ultimately, we've got it down to 2 raised to the negative 2x power equals 2 to the 5th power. And so now check it out. We've got the same base on both sides. Thus, the only way that this equation is going to be true is if their exponents end up being equal. That way, in each case, I'm raising the number 2 to the same power on both sides and thus getting the same thing on both sides. So I need it to have their exponents equal. So I'm going to equate their exponents. So notice I'm not doing like a mathematical procedure like, oh, I'm going to divide both sides by 2 or add a number to both sides. I have to make a logical connection here that this must be true. And then finally, I can divide both sides by -2. And so my answer is x equals -5/2. So a pretty snazzy example. And again, we haven't really done anything just quite yet that really requires a calculator, to solve. I mean, the calculator is not going to help you solve this one, not without using any kind of advanced tricks, and you still have to come in knowing a few things about math in order to be able to solve it. But it looks like today we're finally going to start to get a taste of using the calculator. But we don't get super duper detailed with it. The calculator is really in this class just used to solve or crunch some numbers that are impossible for us to do with pencil and paper or in our heads or anything like that. So let's try out one more real quick. Say goodbye to the screen. Let's try out one more. And let's pick a different color. How about 2 raised to the x plus 4 power is equal to 8 raised to the x minus 6 power. Now, remember our strategy so far has not been to use any kind of advanced techniques. What we need to do is see if we can't re-express the equation in a manner that it's just something raised to the something with the same base on both sides, perhaps raised to different exponents. Because once we get that, then we can equate their exponents. Well, we already have a base of 2 here, and here we have a base of 8. Well, it looks like there's going to be a nice connection here because 2 to the 3rd power equals 8. So you kind of have to make those connections. If I had put a 7 as the base here, or an 11, or a 14, or a 21.8, that's not going to fly because that can't be re-expressed as the same base as this in a reasonably simple manner. So I'm going to leave this part alone. I'm just going to reproduce this part. And now I can rewrite 8 as 2 to the 3rd, and then it's being raised to the x minus 6 power.
Yeah, you can do 2 to something. Or 8 to something, but usually you can go down with the metric.
And so now I can start to solve it. One thing we can do, we can distribute this 3, and we have to distribute it because according to one of our laws of exponents, the 3 gets multiplied to this other power. These two powers multiply together, and it gets multiplied to the entire thing. So our next line then is 2 to the x plus 4 power equals 2 to the 3x minus 18 power. And now, bada bing, bada boom, we have exactly what we want in that we have an exponential equation. Both sides have the same base. So the only way they're going to be equal to each other is if their exponents equal to each other. So the exponents have to equal each other. X going to give it to you. So now we just have a very simple equation to solve. It's just a simple linear. There's no exponents. There's no fancy tricks being pulled here. So, okay, let's solve it. I guess I'll subtract 3x from both sides. I'll also move the 4 over there. And so I'll end up with negative 2x on the left, x minus 3x. Subtracted the 4 over. I subtracted the 3x over, and then negative 18 minus 4 is negative 22. Divide both sides by that negative 2. And you'll have x equals positive 11. And so, bada bing, bada boom, we've got what we want. You could technically check your answer. Well, maybe that can be a bit of a difficult enterprise without a calculator. But if you were to check your answer, you'd plug 11 in for x into the original equation, Shmia unda Shmia. You'd end up with 2 raised to the 11 plus 4. You'd end up with 2 to the 15. So we're just checking our answer. You'd end up, ooh, that's not what I want. You'd end up with 2 to the 15th equals, then 8 to the x minus 6, you'd put 11 in there. 11 minus 6 is 5. You'd end up with 8 to the 5th power. Now, I'm not going to sit here and do 2 to the 15th off the top of my head, but guess what? Starting with chapter 4 here, you're allowed to use a calculator. You're allowed to use a graphing calculator. Now, don't do backflips over the moon because it's not going to help you nearly as much as you think. Because the whole point of this material is that we're solving equations, and it's really just helpful for crunching numbers. But if we were to crunch the numbers, I guess I'll go ahead and do that. I'll use my phone calculator for simplicity, but of course on a test, you're going to have to use either a graphing calculator or do you guys have graphing calculators in the classroom with you? Is there like, yeah, okay, that's what I figured. Yeah, so you can use those graphing calculators. So it may not be a bad idea to go ahead and whip them out. If you guys want to go ahead and pass them out to someone, volunteer to be, I don't know, helper. Yeah, I would go ahead and go grab a graphing calculator right now. What is it? Is it the TI-84 or is it TI Inspire? What's the calculator type?
It's TI-84.
A TI-84? Awesome. Yeah, the TI-84 is super duper cool. So the TI-84 will get you far for doing a lot of the calculations we're going to be doing. So bust out those TI-84s, turn those bad boys on, clear out the screen, and just type 2 to the 15th into the calculator. On another line, type 8 to the 5th into the calculator. And in both instances, you should be getting 32,768. And thus, this is correct. This solution is correct. We tried it out and it worked. And that's kind of the whole point. So with your calculator in your hand, we're going to learn some a couple useful math formulas. A couple useful math formulas. And we're going to talk about one of my absolute favorite subjects of all time and one of the absolute most amazing applications of all of mathematics. We're going to talk about money and compound interest. I'm talking about money and compound interest. It turns out that we need math. Money is all about numbers, right? And so, you're not going to learn about money and not use math. It's just impossible, basically. So, what we know, there's a few things we can know. Interest.
Sorry.
Interest is earned either when money is lended or invested. So we're not going to get super duper into the details on this one. So basically, if your friend needs to borrow $100 for whatever reason, they need gas money, they need some food money, and all the other stuff. $100 can get you. Maybe they want a video game, and I don't know, they're going to borrow it from you. Well, you're willing to lend your friend $100, but you would like to have that $100 for yourself. You're like, no, that's money I could have used to go do whatever with, go buy myself something nice or pay a bill. So if you're gonna have to be without that $100 for a period of time, then you may just expect some money back as like a little thank you or as rent on that money. So what you might do is you might charge something called interest. You might say, and we all have an idea of what interest is probably, but you might say, okay, you can borrow $100, but I'm going to charge you $5 interest every week until you pay me back. So if you pay me back in 10 weeks, you're going to have to pay me back $150 instead of just $100 that you owe me. Well, if you have that case, you're actually doing something called simple interest, which is simply where the amount of money you charge per time period is just a percent of the original amount borrowed. That's not actually how interest works in anything in the real world, in the modern world. Instead, in the modern world, what happens is if you borrow like $100 and they charged you 5% interest per week, then after 1 week, they would take 5% of the $100, which is $5, tack it on, and now you owe $105 if you paid it back a week later. But if you wait 2 weeks, you would end up owing 5% not of the original $100 tacked on. They would take 5% of the now $105 you owe after 1 week and tack that on. And so, we don't really have time to go into uber detail about that. But basically, compound interest means that the amount of interest earned updates with the amount of interest that's already been earned. Simple interest doesn't do that. Simple interest just keeps adding on an amount based on the original principal of the loan, the amount borrowed. Interest can also work another way. You can either, if you're the one borrowing money, interest is working against you. It sucks that you got to pay interest. You're paying rent basically on the money that you've borrowed. But if you're the one lending out the money, well, you are taking a risk that you're never going to see that money back. And I think we all have that friend who will borrow $5, $10 from you for lunch or something. and you're never going to see that money again. You just know that you just love that friend and you're like, okay, here's $10. I'm never seeing it again. We all have that kind of friend. So when you're the one lending money, you expect interest back, not just because you would have liked to have that money yourself, but because there's a risk you're never going to see that money again. And if you're lending out money to lots of different people, you need the people who will pay you back with interest to kind of cover the people who are never going to pay you back. So the more risky you think someone is and the less likely you think they are to pay you back, the more interest you have to charge. You just have to. Um, that's like one of the cornerstones of modern finance. The riskier something is, the more return you expect should it pan out and work. But there's other things you can do. So if you're the lender, that could be seen as an investment for you. You're putting money away, you're not getting to use it right away, but you're hoping that with a little bit of time, it's going to come back to you and it's going to bring some of its friends and it's going to bring back more money than what you started with. That's the basic idea behind investments. Now, lending money is obviously not the only way to invest money. You can buy stocks. The idea behind buying a stock, you buy it now. The company uses that money in order to promote its business activities, to actually run things. And then if the company ends up doing well and their stock value goes up, you can turn around and sell that stock at a higher value than what you bought. And thus you get your money back with some extra money with it. So all of this is governed by mathematics. All of the way that money works is completely governed by mathematics. So let's look at something called the compound interest formula. Let's look at the compound interest formula. A equals P, open parentheses. That's a 1. That is the number 1. 1 plus R over N, that is an N, raised to the N times T power. What the heck do some of these variables mean? Well, let's talk about it. The future amount. A is going to be the amount in the future, the amount the money grows to. P is going to be the principal or the initial amount today. R is going to be the interest rate as a decimal. N is going to be the number of compounding periods per year. We won't go into uber detail about that. I'll just tell you it's usually something you're going to be able to glean very quickly from the information. And then T is going to be the number of years that we invest this money at. So let's break this formula down. According to order of operations, this R over N computation, it has to happen first. This N times T, you got to multiply the N and T together before you do the exponent itself. So we're going to need a calculator for these kinds of problems, which is exactly why I had you bust them out. Well, let's move this over here. Relegate it to the top left corner. And let's do an actual example. I'm going to show you exactly how this formula works. I'm also going to show you kind of the best way to put it into the calculator. It's going to be a big, beautiful formula. So let's say you borrow $1,500 for whatever reason. It could be a personal loan. It could be to help you buy a car. You just had a little bit left from your savings you need to get the car you want. you borrow $1,500 and plan to pay it back in 3 years. So you're going to borrow the 1,500, and then you're not going to make monthly payments or anything. You're just going to pay it all back with interest in 3 years. That's not a very common setup in reality, but maybe if you borrowed it from a friend, that could be the case, or your parents, or your grandparents, or someone else you know, you might do that. Now, the interest rate is 7.8%, percent compounded monthly. How much will you owe? So you're borrowing $1,500. Now, while you have that money in your possession, it's slowly growing and it's becoming more that you're going to have to pay back later. So what we're going to do is this is clearly going to be governed by this formula. It's compounded monthly, so we know it's compound interest. Compounded monthly just means that n is going to be 12 because there's 12 months in a year. Thus, there's 12 compounding periods per year. So let's write out what each of the variables are for this particular setup. And then we'll just plug them into the formula. I'll show you the best way to put it in the calculator, and that'll be good. A is going to be what we don't know. A is going to be the future amount, the accumulated amount, the amount that you're going to owe in the 3 years. So I'm going to put a question mark there, and when we actually do the formula, I'm going to put the variable A into the formula and not a number for it. P is the principal. It's the initial amount, the amount borrowed in this case. R is going to be the interest rate, but we need to express it as a decimal when we actually sit down and do the math. You'll hear it quoted as a percent in reality, but when you're actually doing the math, you're going to need to write it as a decimal. N is going to be the number of times interest compounds per year. What the heck does that mean? Well, that takes its own 5-10 minute explanation. So for now, we're going to take it on a little bit of faith. If it says it's compounded monthly, there's 12 months in a year, so N is 12. It's compounded quarterly, 4 quarters in a year, N is 4. It's compounded annually. There's only 1 annual period in a year, so N would be 1 in that case. Finally, T would be 3 for the 3 years. So this is the best way to approach these problems. You know what the formula should be. That's actually not always easy. In this class, there's not going to be a whole lot of formulas we look at. But if you're taking a financial mathematics course, you would have a slew of formulas, and you got to pick the right one. And then it's useful to write out the variables. Write out exactly what they're going to be. So since we don't know A in the formula, I'm just going to write A. And then I can plug in the numbers. A equals 1,500 times open parentheses 1 plus. Now R is 0.078 over N is 12. We're raising it to the power of 12 N times T, so 12 times 3. So we got to figure out a way to do this. The order of operations says we'd have to do this division first, then add it to the 1. We need this 12 times 3 to happen. Then we raise this to that 12 times 3 exponent. So that's the suggested order of operations. So you could do it step by step. You could do 0.078 over 12, simplify that, add it to 1. You could do 12 times 3, get it to 36. The problem is sometimes this computation here will not lead to something that is simple. In this particular case, it will. But in other cases, you could get a decimal that goes on forever and ever and ever and ever. And you're going to have to round it. And the more rounding you try to do, the more inaccurate your final answer is going to be. So guess what? we can put this entire thing into the calculator all in one go. We can do this all at once, all in one line, hit enter and get our answer. So let me show you how I'm going to do that. So bust out your calculators. Those TI-84s can easily handle something like this. Clear it out or get a nice fresh line that has nothing written on it. And you can actually literally type this directly into the calculator, and you're going to use parentheses. You're going to use another set of parentheses so that the calculator knows to do that 0.078 over 12 computation first. So you're going to put that in parentheses. Then we need to close off these parentheses. You're going to find your caret button, which on the TI-84 should be near the right-hand side of the buttons, like near the clear button, I think. Or no, is it more to the left? Well, find the caret button. It looks exactly like that. You don't even have to use the second button. Then we need to raise it to this power. We want the 12 times 3 to go down first. So we're going to put the 12 times 3 in its own set of parentheses. So it knows to turn that into 36 and then raise that power. So you guys can literally, that's exactly what it's going to look like in your calculator. It may have to line down or something. It may do that for you, but that's ultimately what's going to happen. It's exactly how we can punch it in there. So I'm going to do this computation. You guys probably already have it. I'm going to use my own set of magical tools. So hopefully you guys are getting, and it is a dollar amount, $1,894, and we're going to round to the nearest cent, so 2 decimal places. They want to know if they'll be able to use TI-84s on the test. My friends, my wonderful students, lift your voices in excitement, because yes, you will be able to use the TI-84s on the next exam, because there's going to be problems on that exam that you can't do without the TI-84. So yes, you'll be able to use the TI-84s on the test. Hallelujah. You won't be able to use them on the final exam, because in the final exam, any problems we use from chapter 4 are going to be stuff that you can do technically without a calculator. They're not going to require heavy number crunching like this one was. So yes, my friends, you will be able to use it though on the 4th exam. And so that should be cause for great excitement. You'll probably realize that at the college level, they don't want you to use the calculator. They want you to use it as little as possible. And there's good reason behind it. But simply these numbers you cannot do. I can't raise something to the 36th power by hand in a reasonable time frame without any mistakes. It's just not going to happen. So we need to start using the calculator. Okay, great question. So basically, hopefully you're getting the 1894.03. So in 3 years, you're going to owe $1,894.03. How much of that will be interest? Well, that should be fairly logical. We have to give 1894.03. We initially only were borrowing $1,500, so that means $394. I'll put a dollar sign in front of it. And 3 cents of that is going to be actually interest. The other 1,500 of it is just going to be me repaying my loan. Now let's look at something really cool. Let's just play with one little thing in the numbers. So let's just play pretend. So if you pay it back in 3 years, you only have to pay $394.03 in interest, which you'd rather not, but compared to the $1,500 you borrowed, that's not horribly unreasonable. That's not completely out of bounds. But let's say you were paying it back in 35 years. Now, would you ever borrow money for 35 years like that, a single sum, and not make monthly payments? Probably not. So we're just kind of playing pretend with it. Oops. We're just kind of playing pretend. So all we're going to have to do, we're going to have to use a 35 instead of a 3. So we just have to slightly update things that we just did, but not a whole lot. 35 instead of 3. And then down here, 35 instead of 3. That is definitely going to change our final answer. So now try this in the calculator. Try this. And if you're crafty, you know you can bring up the previous line you just did and make edits to it before you hit enter. Or you can just type the whole thing out again. And you're going to be shocked and appalled at how much money you're going to owe in this particular case. I'm doing the calculations myself. So if you wait 35 years to pay the loan back, you're going to owe $22,797.04. I'm going to tell you right now, we didn't make a mistake. We did not screw anything up. No. That is exactly correct. That's very reasonable. Yeah, you owe almost $23,000. So, I mean, if you calculate the interest, maybe we can do that off the top of our heads. It's going to be $21,297.04 interest. Oh my goodness. Now, yeah, 35 years is a very long time, but to have that kind of burden laying out behind you is really scary. So imagine student loan debt. Imagine student loan debt. I mean, you'll borrow money for however long you're in college if you go into student loan debt, and then you turn around and you have to pay it back. Now, you won't pay it back all in one lump sum 35 years later, but you're going to slowly chip away at it. You're going to make monthly payments maybe after you graduate. And over time, I mean, if it takes you a while to pay off that student loan debt, you could be paying more in interest than you ever borrowed. If you borrowed $20,000, but you take a while to pay it all back, you may end up paying back $45,000 total dollars, in which case $25,000 was interest for a $20,000 loan. That's ridiculous. Think about a house. Think about buying a house, getting a mortgage. You could, if you had an exorbitant interest rate because you bought a house in the 90s when interest rates were, through the roof. If you bought a house back then, I mean, there was 10 to 15, even up to 20% interest rates on home mortgages, which is out of this world. If you buy a house today, you can get an interest rate between 2.5% to 5%, somewhere in there, most likely, and that's a really good rate. So if you bought a house back then, I mean, you could buy a $200,000 home and end up paying back over $800,000 over 30 years to pay it off, which means you spent more than 3 times the house's value when you bought it just in interest. Compound interest, do not sleep on it. Do not take it lightly. Do not think it's not all that important or valuable. This is entirely the state of money today. It's how it works. What's interesting is that in kind of ancient Middle Eastern culture, in the Islamic world, it was considered immoral to charge interest on a loan. It was considered very immoral if you were, lending money to your friend or your brother, someone that mattered to you, someone who's important, and you charge them interest. I mean, that just sounds kind of mean. That sounds crappy, really, like a bad thing to do to someone else. So that's kind of the view of interest, is that it's evil almost. Of course, things have changed. The days are different now, but that's kind of why interest sucks. Of course, if you're the one benefiting from interest, you might just say, oh, I don't think it sucks. So anywho, that's my little rant. The last thing we'll look at, what if, and we got a lot to delete here. What if we had a case where interest was always compounding? That is, it compounded an infinite number of times per year. Well, you might say, well, n is the number of compounding periods per year, bruh. So like, I'm just gonna go in here and like I'm just gonna like plug in infinity. And yeah, I'm just gonna go put infinity in my calculator. Well, that's not quite gonna fly. That's actually theoretically not too far off from what the math behind it actually works. You would end up using a limit though instead. Also, your calculator probably doesn't have the infinity option. It probably does not have an infinity button, or if it does, it won't. But if it did, in theory, it would have a huge warning sign saying you may not know what you're doing when you're using the infinity button. So instead, it turns out if you did want to compound interest an infinite number of times per year, you're actually going to need to use a different formula. You're going to need to use a different formula. So, whoops, no, don't move that. Let's change up our formula a little bit. So this is a formula that is necessary for interest compounding a finite number of times per year. But now we're going to use another formula, and this is actually, ironically, even though it's useful in much less cases, it would seem, this is actually a much more famous formula because this actually governs a lot of things in mathematics. This is actually governs things like how objects heat up or cool. If you put a really, really, really cold object like an ice cube into a room that's room temperature, this formula could actually be used to decide what the temperature of the ice cube will be after so much time. But we're not going to use it in that application. Sometimes this is called the PERT formula. A, P, and R are all the same. N, though, is not there because we're assuming n to be infinity. So it doesn't even show up in the formula. The formula has already adjusted for that. So this is used when interest compounds continuously. N is not needed because it's already been kind of factored in or thought about when you have this formula. Now you're probably saying, Josh, what is the E variable here? Oh, E is not a variable. Just like pi 3.14159 dot 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 dot, just like pi is an incredibly famous constant in mathematics that tells you the ratio between a circle's circumference and its diameter. E is another super uberty duber famous constant that is just set. E is about equal to 2.71828. And just like pi, E actually goes on forever and ever and ever and does not have a repeating pattern. E, in fact, is said to be, that would be, make it irrational. Your calculator has E already built into it. Because E is so famous, your calculator already is there on day one and knows what E is. So we'll just do one very quick problem with this. We won't linger on it. So now let's say you lend out $14,655. That's quite a bit of money to lend out. You could have bought a car with that or something else. So you're going to expect when it's time to pay you back, you're going to expect that money to come back with some of its friends, and you get more money back. So you lend out $14,655 at, let's put an exorbitant interest rate. Let's say you're just feeling really mean. 25.5% interest compounded continuously. So it's compounded continuously. It automatically triggers the use of this formula. Sometimes it's called the PERT formula. So you're going to lend this out. 25.5% interest, kiddos, is very, very high. You're talking credit card interest at that point, and credit card interest is predatory. I mean, credit cards are, sometimes they're necessary, and sometimes you can play their credit card reward systems against them and never pay a dime in interest, but get all kinds of rewards from them. But they're trying to trap you with it, and this is a ridiculous interest rate. If you were to ever borrow money at this interest rate, I would try not to. I would try to get into a different loan type that comes with much lower interest. What's even worse is, and maybe you've been there where you've had to get one, so I'm not ragging on the individual. But if you ever go get a payday interest loan, those are wolves in sheep's clothing. They'll be nice, they'll shake your hand, they'll say, "We're doing you a big favor lending out this money for you." What a payday advance loan is, okay, I need money now, I got to pay my rent. I don't get paid for another week. So this company comes in and they say, "We'll give you an advance on your paycheck, but we're going to charge you interest whenever you do get your paycheck and have to pay us back." Guys, there are payday advance loans that will come in at, goodness, 500% interest. I am not kidding. That is literally something that has happened. I mean, the U.S. government has had to step in and really, really regulate those kinds of loans because that's absolutely out of the question. Sorry about ranting. I love ranting because I love talking about money. Money's fun to talk about, and I think it's kind of the most immediately applicable stuff we're going to learn in this course. So anywho, you lend out $14,655 at 25.5% interest compounded continuously. You will be paid back in 10 years. So this can almost be seen as an investment. You're able to part with this money for now because you're hoping in 10 years you're going to get so much more back, and then you can do more with it. Think about like a retirement fund. If you know you're not going to retire for 30, 40 years, you start saving money now, it's going to come back in greater amount. How much will you be paid back? How much will the person who's borrowing from you owe you? Well, you're going to use this formula. We'll write out our variables real quick. A is going to be the future value, we don't know. P is going to be the principal on the loan, $14,655. R is going to be the interest rate expressed as a decimal. Make sure you don't do 0.0255. It's 0.255 because if you move it 2 places over, oops. And then finally, T is the number of years. It's going to be 10. And now when we plug things into the formula, A is going to be equal to 14,655 times E raised to the power of 0.255 times 10. This one I think is going to blow your mind a little bit as well. In the calculator, you can actually write it like this. On a clear, fresh, blank line, you can write 14,655. Go ahead and hit times. And then your calculator in the bottom left should have an E raised to the button already, meaning that you can hit the second button and then hit the proper one there, and it'll automatically do E caret, and it'll open a parentheses for you. That's awfully convenient because that's exactly what you need here. Your calculator should also just have an E button already on there, you may need to hit the second button. You may need to hit the second button. In fact, let me just look that up for you. Let's look at a picture of a TI-84. Look at the buttons. Just give me a picture, please. Yeah, so if you want to bring up that E raised to the caret button thing, hit the second button at the top left. What that does is it's kind of like a shift button that then lets you press anything that's blue. And then go down and hit the LN button that's on the left-hand side of the calculator towards the bottom. And what that really does is because you already have second, it's not actually going to put LN in, it's going to do that E raised to the thing for you. And so it should give you all this here. It'll automatically open parentheses, so to do 0.255 times 10, then close the parentheses. And that should take care of everything you need all in one go. It'll completely finish off the problem for you. Hit enter. So now I'm going to do that with you real quick. I'm going to use my own tools. Oh my goodness. This is going to blow your mind. I am not lying about this. I am not lying one bit about this. $187,688.11. Wow. Wow. Let that sink in for a moment. We had to part with that money for 10 years, but it came back to us more than tenfold. That is ridiculous. That's ridiculous. I'm going to tell you right now, a 25.5% interest rate is exorbitant. It is over the moon, out of this world, ridiculously high interest. It doesn't sound terrible. 25% is only about 1/4 as a fraction, but it is terrible. It is terrible. And this all has to do with exponents, literally because these formulas here require exponents in order to work them. So that was just a little bit of talk about money, and talking about money I think is a lot of fun. If you ever decide to go into the investing world, or if you ever decide to learn a thing or two about finance, which I would strongly suggest you consider it. If you're ever going to do that, you're going to not only revisit these formulas, you're also going to go into an uber level of detail with them. Because again, these formulas absolutely are what's going on. But we must digress and move on to the next section. We're going to go to section 4.3, which is logarithmic functions. Logarithmic functions. Now, maybe you've heard of a logarithm before, maybe you haven't. There's a really, really corny pun joke, a logarithm. You know what? I'm not even going to say the joke because I hate it so much. It burns my blood, so raises my blood pressure. So I'm not gonna make the corny pun joke. It's not funny. Don't think, oh, he's holding back some good stuff from us. No, it's terrible. It's not a funny joke. So first of all, we have to ask ourselves, what the heck is a logarithm? That's a weird word, by the way, logarithm, but it is the word that's used. I don't know why it's used, actually. I kind of see the word arithmetic in there, logic maybe, but I don't know why it is used. Excuse me. Anyway, we learned back in section 4.1 about inverse functions. For instance, if you square a number, the inverse of squaring is to take the square root. If you multiply a number by 3, the inverse is to actually divide by 3. In the same vein, exponents and logarithms are the exact same idea. That's their relationship to one another. A logarithm undoes the effects of an exponent and vice versa. So the logarithm is the inverse of the exponential. That's exactly what it is. It's basically, it's designed then to undo the effects of an exponent or to perhaps figure out an exponent that's necessary for a certain situation. So that's interesting. An exponent just says, take this number, raise it to this power, what do you get? A logarithm says, for this number and this number, what power do you have to raise the first number by in order to get the second number? So the logarithm's kind of seeking out the exponent that's required. So it's almost like a deconstruction of the exponential equation. So we have to make a definition here for the logarithm. And so we have to use a bunch of stuffy sounding words in the immediate sense. For all real numbers y and all positive numbers a and x, with a not equal to 1. Yeah. Oh my goodness. No good way to do that. A not equal to 1. There we go. Slice the Gordian knot in two. Here's how it's going to work. You're going to say y equals. You're going to use log. That's not 1 and 0 and then a g. That's a log. Now, the logarithm is going to have a base. Just like exponents have a base, a logarithm has a base. We're going to say log base. You're going to write it down there as a subscript. You're not saying log times a. The log itself, just the word log, is not a number. It's not something that can be multiplied. The log is telling us that this specific operation is going down, but it is not something that's an actual number being multiplied in there. It's kind of like when you use sine and cosine. If you say sine of pi over 2, you're not saying sine times pi over 2. You're saying that pi over 2 is being plugged into a sine function. Similar thing here. This is how you can write a logarithm. Y equals, this is red. Y equals the log base a of x. That's how I would literally say it, the log base a of x. And I'm even going to gussy it up a little bit. Look how pretty this logarithm is. It's okay. So the log base a of x, and it turns out the logarithmic function, the logarithmic equation, is just a reformation, not a Protestant Reformation. It's a reformation of an exponential equation. It's equivalent to this exponential equation. X equals a raised to the y power. So notice what's going on. This equation in spirit is the same as this equation. Now this second one here, this one in green, this exponential equation, that's something we're comfortable with already. You're just taking some number, raising it to a power, and then you're just figuring out what that comes out to. This could be 8 equals 2 to the third power. So y is the exponent here. Over here, y is the thing that the logarithm is equaling. It's what it's spitting out. So now let's zoom in on this. When you see a logarithm, what a logarithm is doing is saying a, the base of the logarithm, raised to what power is going to give me this number up here, x. And sometimes you can see the x written in parentheses. And it's not a superscript or anything, so let me just slightly adjust this. It isn't a superscript. It's the argument of the logarithm. And we'll look at several examples here in just a moment. But ultimately, the logarithm wants to know what exponent the base needs to be raised by in order to produce the argument or the x value of the logarithm. It's saying a to what power gives me x. That's a completely different idea. Here, we know what the exponent is, we know what the base is, and we're just raising the base to that exponent. It's almost like sometimes you'll plug it into a calculator, or it's just a computation that's very easy to do. Here, no, you got to think a little bit. You got to figure out what exponent is required to raise a by in order to get this x thing. So pretty wild stuff. A few notes, y and x and a all have to be real numbers. So again, we're not really dealing with I here. I was just kind of something we did really early on. The base a has to be strictly positive. It says all positive numbers, a and x. So the base has to be positive. The argument of the log, the x, also has to be positive. Also, we don't want the base to be equal to 1, just like we didn't for an exponential equation. And there's a lot of good reasons for that. Okay, so let's put this up here near the top. This is going to be our kind of ruling idea. Let's just look at a few examples. If I write log base 2 of 8, if I write log base 2 of 8, I need a little more room. What I'm asking for is I'm saying 2 raised to what power gives me 8. I need to know the answer to this logarithm is going to be the exponent required to raise 2 by in order to produce an 8. Well, you can probably see that that's going to have to be 3. And that's exactly right, because 2 to the third power, 2 times 2 times 2, is 8. Well, this is equivalent, just a little double arrow. This is equivalent to the exponential equation, 2 to the third equals 8. Next up, so all we're doing is we're just making these connections here. What's the connection between everything? Another one, we'll just look at a couple examples here. 10 raised to the fourth power is equal to 10,000. That's a true statement. Let's rewrite that as a logarithm. We'll just say it's equivalent that is equivalent to saying the log base 10 of 10,000 is equal to 4. Ten to what power gives me 10,000? The number 4 will do it. So all we're doing is we're seeing the connection between a logarithm and an exponential statement. Let's look at a couple more. We'll jazz it up a little bit. If you have the log base 17 of 1. 1 is your argument. You're saying 17 to what power gives you 1? Well, that's going to have to be the 0th power. And that's equivalent to saying 17 to the 0th power equals 1. That's exactly right. Because raising to the 0th power always produces a 1, as long as you don't raise 0 itself to the 0th power. That's the only kind of exception. Finally, one more. The log base 3 of the fraction 1 over 81. You look at that and you're like, well, I know that 3 to the 4th power is 81. So is there a connection there? Yes. In order to turn it into a fraction and put the 81 on bottom, the exponent would have to be -4. And so this is the same as saying 3 to the -4th power equals 1 over 81. So that's pretty cool, pretty cool. If you don't believe me here, well, when you raise 3 to the -4th power, that really becomes 1 over 3 to the +4th power. That's what negative exponents do. And then 3 to the 4th is 81, so it's just 1 over 81. So that's how that works. So we're going to be using negative exponents. Remember, the restriction was only on a and x in the logarithm. The restriction said a and x had to be positive. A could not be 1. The only restriction on y is that it has to be a real number. So the exponent itself can be negative because negative numbers are real. So you have to be careful. What I can't do is I can't take the logarithm and I cannot use a negative base like that. There's reasons for that. It turns out, well, let's just say there's reasons for that. Logarithms are going to be very particular about the exponent and the bases and what they can come out to. Logarithms are very particular. So no negative base is allowed with a logarithm, just like when we did an exponential equation and we tried to graph it, whenever we used a negative base, it created problems. The graph went away. It becomes a series of singularities, which is the name of my band. So just like for exponential equations, logarithmic equations, we are not going to use a negative base, but your exponent can come out negative. So with all this in mind, we can work an example problem, a very simple one, and we're going to solve the log base x of the fraction 8 over 27 equals 3. Wait a minute, Josh, how can we solve this? Do we divide both sides by log? Well, no, because log is not a number itself. How do we solve this? Well, in a lot of logarithmic equations, try rewriting as an exponential. Oh, okay. So let's think. The exponential equation for this would be x to the 3rd power equals 8 over 27. And perhaps that's not too horribly comforting at this particular juncture in time. But what I can say is, well, my variable is being raised to the third power. So I can solve this. Let me give it a little more space here. I can solve this by taking the cubed root of both sides. And then take the cubed root of there. And that is going to be true. You're just going to get x equals. Now we're taking the cube root of 8 over 27. We can think of that as the cube root of 8 over the cube root of 27. And I'll bet you $5 it'll come out clean. If this was 7 here and this was like 28, maybe it probably wouldn't come out clean. But now, instead, the cube root of 8, we need a number which multiplies to itself 3 times to produce 8. And it just so happens that that comes out cleanly as a 2. Cube root of 27, we need a number that multiplies to itself 3 total times to produce 27, and that'll be just 3. So x is equal to 2/3. Put another way, the log base 2/3 of 8 over 27 is equal to 3. As an exponent, that's just saying 2/3 cubed equals 8 over 27, which makes sense. You'd cube the top, get 8, cube the bottom, get 27. Okay, that's all I got for you today. You got less than a minute to go until class is up.